Hi, I'm Ryan Michael, VP of Engineering at Kaskada. Kaskada is a time-based feature engine that adds a new way to process event-based data to your existing data processing tools and allows behavioral machine learning models to be built and deployed 26 times faster than using traditional compute engines. Today I'm going to show you how Kaskada fits into your existing infrastructure and some of the ways that it helps quickly get from idea to production model by walking through an example. We'll look at how we can use events generated by a game to predict user churn, but behavioral models aren't specific to gaming. Kaskada can improve the workflow of any time-based model. Traditional compute engines are good for things like grouped aggregations, and they can tell you a little bit about the current behavior of demographic groups or cohorts. But the ability to revisit the past is central to understanding behavior, and traditional tools don't know anything about time. They tell you the answer to a query, but what you need to know is the story of how that answer has changed over time. Looking at each user's events as a timeline lets you see that user's story. This user likes to brag about his conquests, and that user pays for upgrades when they're frustrated. Kaskada manipulates streams of values. These streams tell the story of exactly how the result of a computation changes over time. In this example, we'll read raw events directly from tables stored using Apache Iceberg, but Kaskada supports loading data in multiple different ways. We're ready to start using Kaskada to build training datasets. Kaskada's query language describes features in a simple syntax that's designed to express time-based computations. Aggregations can be windowed in familiar ways like daily or monthly, or in ways that can be almost impossible with traditional compute engines, for example, sliding over the previous 5 values. Aggregations are always grouped by entity, but you can easily change each value's entity or look up the value of another entity. And when you do this, the results are always point-in-time correct. This set of features can be used both for training and prediction. So let's create a named view that contains the features. We'll refer to this view in a minute when we produce a training dataset, and then again later when we're ready to start populating a feature store. ML models must be trained on representative examples. And for behavioral models, this means examples that reflect the specific points in time that the model will be used to make predictions. In this example, we're observing our features every time a user logs in, and then waiting 7 days to see if the user churned. Time travel in Kaskada is not only data dependent, you can safely combine values computed at different points in time, as in this example where the value being predicted is only known after the prediction has been made. In these results, each row reflects a training example. It's produced at a single point in time for a single user. We've observed each user's story at the specific points in time that are meaningful for the model that we're training. Computing point-in-time feature values like this with traditional engines is difficult, slow, and error-prone. The power of Kaskada's query language is that it allows you to describe when to compute values as part of your query. So iteration is instantaneous, and you don't end up spreading model logic across processing jobs and orchestration tools. Kaskada's unique processing model means that computing the current value of any query can be done incrementally. Given a reference time, Kaskada will only return feature values that have been affected by events after that time, and the cost of the computation scales with the number of new events. Best of all, your feature values always reflect the full history of all your data. Building on this incremental compute engine, Kaskada gives you the ability to actively push changes to a query's results to external key value stores. This is a feature we call materializations. Let's create a materialization to actively push our model's feature values into a Redis cluster. Now, we're ready to make predictions in production. Redis will always contain the current value of all of our model's features for every user. Wouldn't it be nice if deploying the first version of a model was the end of the story? Of course, in reality, we need a way to manage changes to models and features as they evolve over time. And Kaskada is designed with ops in mind. Kaskada provides tools for declaratively managing your resources as code. Using the Kaskada command line interface, you can export the current state of your infrastructure to see exactly what resources have been created, or you can synchronize your resources with the contents of a file. The CLI is easy to integrate into a CI pipeline and allows you to use your existing code review and governance practices to manage changes to Kaskada resources. We've just looked at how Kaskada fits into a typical ML flow, but we've only scratched the surface. If you'd like to learn more, go check out our docs. You'll be able to try it out yourself and see the power of Kaskada's unique approach to data processing.